Welcome back for another episode of Anomaly Watch. Today I have an update on a peculiar anomaly in the behavior of an atom that could be evidence for a dark force, as the headlines put it. A new experiment looked for the anomaly and confirmed it. This anomaly is young. It was first detected in 2020 by a group at MIT. They studied atoms of ytterbium, which is a metal with atomic number 70. The anomaly was originally at roughly 3 sigma, but it's now jumped to a stunning 23 sigma. Ytterbium is not a very common element unless you work in nuclear physics, where it's super popular. This is because ytterbium has a special property. Like most elements, it has several isotopes. That means its atomic nucleus can have different numbers of neutrons. Now, if you add neutrons to the nucleus, that makes the nucleus bigger, but keeps the electric charge the same. This very slightly changes the electron energy levels in a way that depends on the properties of the nucleus. And ytterbium just so happens to have the perfect number of neutrons and protons in the nucleus to make its electron energy levels very sensitive to changes in the neutron count. This means that if you compare different isotopes of ytterbium with each other, you learn a lot about the nuclear structure. This is why physicists like to hit different isotopes of ytterbium with laser light at different frequencies and then check what comes back. The laser probe tells them where the electron energy levels are, which in return tells them something about the interaction between the nucleus and the electrons. Then they compare the responses of different isotopes, which is called the isotope shift. This isotope shift should have a predictable dependence on the frequency, but here's the rub, the data don't comply. The 3 sigma deviation which the MIT guys found in 2020 isn't much. It could happen with a chance of 1 in a few hundred just coincidentally. It's not the thing that keeps you up at night, unless ytterbium is your best friend. So of course nuclear physicists looked into this closer. The authors of the new paper poked ytterbium again, but this time they used a super precise measurement technique called a frequency comb that's great for teasing out fine details of a light spectrum. Frequency combs even got a Nobel Prize in 2005. And here's the banger. Using this technique vastly increased the mismatch between data and predictions. You can see this here in this figure, where the red line is the prediction and those are the data points. The error bars are increased by a factor of 200 because otherwise you wouldn't see them. There could be multiple reasons for this, but either way you look at it, they say, there needs to be some extra contribution in addition to the nuclear physics that they did already use, which is in nuclear deformation. They write in the paper that they deduce a 23 sigma preference for more than just the nuclear deformation going on, and that this leaves open the possibility of a new boson being responsible. So they don't say that this must be a new particle, but that a new particle would explain the mismatch. They calculate that the new particle would have to be one of medium mass, with a mass somewhere in the range of a few mega electron volt. You may wonder now, well, but why then have we only seen it in ytterbium and not elsewhere? The reason has not to do with the boson, but with ytterbium. This particular chemical element just so happens to be extremely sensitive to any sort of interactions at nuclear scales. It's quite plausible that if such a boson exists, you'd see it first in such an experiment. If this deviation is due to a new boson, and that's a big if, this would be huge. It'd mean there is an additional interaction not accounted for by the standard model. It could solve a lot of problems, such as dark matter or the unification of forces. This is why it's sometimes called a dark force, because it's what we'd expect from a force that stems from dark matter particles. However, nuclear physics is much more difficult than particle collisions, because atomic nuclei are made up of so many individual particles. It could be that this strange signal just comes from some badly understood behavior of the atomic nucleus, also new physics in some sense, but not such a groundbreaking revelation. Still, I think it's worth keeping an eye on. The element ytterbium, by the way, is named after the Swedish village Ytterby, where it was first discovered. Ytter means outer and by means village, so the proper translation would be outer villagium, which sounds like a self-help retreat for a brain cleanse. Though personally, I suggest that if you need a brain cleanse, you stare at a text form. Works for me every time. Why does space have 3 dimensions? Did God only have 3 fingers to count on? No one knows. This is why physicists have for more than a century considered the possibility that space has more than 3 dimensions. This idea has had its ups and downs, but today's news is definitely an up. A group of physicists say that extra dimensions might explain how our universe grew to this enormous size, what dark matter is made of, and also make some new predictions that could be testable soon. This is because they say the additional dimensions can lead to a cosmological stasis, a temporary phase in which the universe expands, but nothing in it changes. Let's have a look. If our universe has additional dimensions of space, they need to be small so that we haven't yet noticed them. They need to be rolled up to a small radius, or if you want to hear the technical term, and I just know you want to, they need to be compactified. Yes, that's also what you do with the extra dimensions in string theory, but this new theory comes without strings attached. The thing with these additional rolled up dimensions of space is that they can make one particle appear like an infinite number of particles. This is because quantum physics has taught us that particles are also waves, and if you have a particle that can extend into these extra dimensions, then its wave must go around the dimension and then fit together with itself. This means that its wavelength must fit to the size of the extra dimension like a standing wave on a jumping rope. And there are infinitely many ways to do this depending on how many periods of the oscillation you can fit in. So each time you have a particle that can go into the extra dimensions, it'll behave like an infinite number of particles. This is also called a tower of particles, and it's the main ingredient to the new theory. The authors now conjecture that one such particle exists that can go into the extra dimensions and create this tower. The details of the particle don't matter much, but it's not a particle that we have already discovered. They say that if you have any particle that creates such a tower of modes, and you start the tower out in the early universe by giving it some energy, then this energy will gradually decay down the tower. And while this happens, the gradual decay creates pressure that expands the universe very rapidly and very steadily. This is the cosmological stasis. The universe expands, but in it nothing changes. Matter doesn't clump, radiation doesn't dilute, everything remains the same, until this tower of particles runs out of its initial energy. Then the rapid expansion ends, and the matter in the universe begins to clump and form stars and galaxies. It's an interesting idea because, you see, physicists have long suspected that after the Big Bang, our universe must have undergone such a phase of exponential expansion. Concretely, they think it must have increased its size by more than 26 orders of magnitude within a billionth of an attosecond. And you thought pregnancy was bad. The exponential expansion is called inflation, and physicists say it's necessary to explain why the cosmic microwave background looks the way it does. I'm forever on the fence about it. On the one hand, I agree it's a useful theory to calculate some features of the cosmic microwave background. On the other hand, I'm pretty sure that it isn't the only theory that'll do that for you. The biggest problem with inflation is that we don't know what caused it, and we don't know how it stopped. And this is where the extra-dimensional particle tower comes in. It gives rise to this cosmological stasis, which is a temporary phase of exponential expansion, and that naturally stops when all the initial energy has cascaded down. Better still, once cosmological stasis stops, the particles from the tower don't disappear. They linger around and form dark matter. It's a particular type of dark matter called warm dark matter that physicists have considered before. They just didn't know what it might be made of. If dark matter is warm, then loosely speaking, it doesn't clump as well as the more common type of cold dark matter. The difference between cold and warm dark matter is difficult to infer from observations. However, the authors say that their theory could be testable in other ways. The exit from the cosmological stasis would leave behind a characteristic gravitational wave signal and also telltale signs of weird correlations in the cosmic microwave background, both of which might be measurable with upcoming experiments. So what are we to make of this? To be shockingly honest, I think this is nonsense. It's mathematical fiction, a combination of speculative ideas that make for an even more speculative idea. The most interesting thing here is that people get paid for working on this. But what do I know? As I said, the idea of extra dimensions had its ups and downs. So maybe the real problem is that the more dimensions you have, the more difficult it becomes to tell what's up and what's down. Americans are very upset. They haven't quite been the same since December, when the Chinese company DeepSeek popped up with an AI model that easily competes with the best American models. But this was only the beginning. It's foreseeable that there'll be many more DeepSeek moments. Just the other week, Chinese researchers presented a quantum computer that rivals the best American one. A Chinese company released an autonomous AI agent, which became wildly popular overnight. The Chinese government invested another $100 or so billion into new technologies. They're rapidly building up their own semiconductor industry, and at that rate, they'll be opening a wormhole to Andromeda next week. I have a quick summary. This should have been big news, but it wasn't. Just a week ago, researchers from the University of Science and Technology of China in Hefei announced remarkable progress with their quantum computer. It's called Suoxiongxi 3 after Suoxiongxi, a famous Chinese mathematician, and it works with superconducting circuits like Google's. In December, Google had reported that they were able to perform a calculation in 5 minutes. That would have taken a supercomputer 10 to the 25 years, though what the media reported instead was that they found evidence for a multiverse. The new Chinese system also has 105 qubits, the same as Google's Willow. The analyst firm Global Quantum Intelligence has found that the Chinese computer is basically on par with Google's in all measures, at least in this universe. The quantum computing race is definitely heating up. And then on March 5th, the Chinese startup Monica released Manos AI, which they described as the first general AI agent released to the public. It's designed to handle tasks like trip planning, stock analysis, and report creation without human guidance. Also, they say in their demo, and yes, that's very similar to the GPT operator demo, which we saw in January. At the moment, Manos is only accessible with invitation codes that have been traded online for prices exceeding $1,000. Many of the first users have been impressed, though some have claimed it's built on Anthropic's Claude. Next up, we have an announcement from the Chinese government that they've created a government-backed investment fund of approximately $138 billion that includes quantum technologies and AI. Going by previous funds they've created, the government will probably contribute about 20 to 30%. They already have several such funds for the semiconductor industry. And speaking of semiconductors, Chinese researchers are doing a lot of work on generating the next generation of microchips. For one thing, they're pretty close to having their own machines for extreme ultraviolet lithography. That's a method of producing microchips with extremely fine details. At the moment, the Dutch firm ASML is the only producer, but it seems like that monopoly is about to end. The Chinese are also developing atomic scale manufacturing, which is basically the next level of engineering. Whatever the next generation of smaller chips looks like, it's likely to involve this atomic scale manufacturing. Most of the research we see coming out of China at the moment is applied. They're very output oriented. We also see this in terms of output in the number of scientific articles. On that count, Chinese research output has overtaken the US-American one already in 2015. In 2020, China took the lead in top-cited papers, and according to the South China Morning Post, also has the most top scientists. Yes, there are reasons to be somewhat skeptical of what the Chinese media says about China, but I think Americans finally understand that they can't just put it all down to propaganda. All of this is not so terribly surprising if you take into account that China's population is more than 4 times that of the United States. But if you take that into account, it's also foreseeable that they'll likely pull significantly ahead in the coming decade. I used to rarely talk about Chinese research because it was too difficult to find any good information about it. But also in this regard, the situation has completely changed in the past years. On the most basic level, the quality and frequency of English press releases from Chinese institutions has noticeably increased, and they're also more present on social media websites that we Westerners frequent. The Chinese space station, for example, has a Twitter account. I find this an interesting development because it seems that as China makes advances in science and technology, it's also becoming more open. Okay, I'm not a quantum computer, but I wanted to be on record that I summarized in 5 minutes what would have taken Lex Friedman 10 to the 25 years. Is that evidence for a multiverse? Let me know in the comments. Artificial general intelligence. I think I can finally see a path for how we'll get there. Let's have a look. There's no consensus definition for what exactly artificial general intelligence, AGI for short, means, but I think most people mean intelligence comparable to that of humans or above. And the general sense I'm getting from people in AI research is that AGI is a few years away, maybe a little more, but likely less than a decade. Demis Hassabis, chief executive of Google DeepMind, for example, has recently said that AGI is probably just a handful of years away.
We've been working on this for more than 20 plus years. We've sort of had a consistent view about AGI being a system that's capable of exhibiting all the cognitive capabilities humans can. And I think we're getting, closer and closer, but I think we're still probably a handful of years away.
Sam Altman, the CEO of OpenAI, wrote last year that it's possible that we'll have superintelligence in a few thousand days. And last month, he added somewhat vaguely on his blog that systems that start to point to AGI are coming into view, where he defines AGI generally speaking as a system that can tackle increasingly complex problems at human level in many fields. If nothing else, we can credit Altman for single-handedly keeping blogs alive. Dario Amodei, the CEO of Anthropic, doesn't like the expression AGI because to him it's more of a marketing term, but he also believes that the AGI he doesn't want to call AGI is just a few years away.
AGI has never been a well-defined term for me. I've always thought of it as a marketing term, but the way I think about it is at some point we're going to get to AI systems that are better than almost all humans at almost all tasks. The term I've used for it in an essay I recently wrote is a country of geniuses in a data center. It's a sort of evocative phrase for all the power and all the positive things and all of the potential negative things. That's the thing that I think we are quite likely to get in the next 2 or 3 years.
Generally, people in Silicon Valley say they feel the AGI. Kevin Rose, who clearly spends too much time talking to these people, wrote in a recent New York Times essay that the first claims of AGI will come probably in 2026 or 2027, but possibly as soon as this year. Then again, people who work on tech developments tend to be, shall we say, somewhat over-optimistic. The cognitive scientist Gary Marcus, who has a somewhat more grounded outsider opinion, recently wrote, "I think there's almost zero chance that artificial general intelligence will arrive in the next 2 to 3 years, especially given how disappointing GPT 4.5 turned out to be." What he means is that GPT 4.5 was basically very little, very late. But even Marcus thinks that AGI will come. It's just that the current models, large language models or transformer models, aren't going to get us there. As I said previously, I agree with him on that. Honestly, the idea that you can breed intelligence from text seems somewhat idiotic to me. You could say, well, what does Sabine know about intelligence? Fair enough. I mean, maybe I'm not even real, but by now most AI experts agree that the current models are unlikely to get us to AGI. You can tell from a recent survey that was conducted between summer 2024 and spring 2025 by the Association for the Advancement of Artificial Intelligence. They asked almost 500 AI experts and found that 3/4 think that scaling up current AI approaches to yield AGI is unlikely or very unlikely to succeed. A good illustration for the problem is this multiplication table. That shows how often one of the recent GPT models is successful in multiplying large numbers. The more the models have been trained, the better they've become with increasingly large numbers, but they still haven't learned the pattern. Now, on the one hand, you can say, okay, but this problem is easy to solve. You just need to switch to a math software for purposes like this. Okay, but on the other hand, this shows that even after being trained on huge amounts of data, large language models don't develop an understanding of how multiplication works in general, despite the fact that they have access to countless textbooks that explain how it works and that they can write code to multiply numbers. Clearly something isn't clicking into place. But if not those models, then what? There are two developments that I think are likely to become more relevant in the near future. The one is to bring in some sort of symbolic reasoning that's basically a logical core. If you combine the symbolic reasoning with neural networks, it's called neurosymbolic, and it's what DeepMind's AlphaProof used to achieve its impressive maths abilities. AI researchers have tried to connect symbolic reasoning to large language models with what's called knowledge graphs. These are basically attempts to break down text into its logical relations. I think this'll come and it'll be an improvement in reasoning abilities, but ultimately not get us to AGI, because most text isn't logical. It'll not solve the underlying problems with large language models. So symbolic reasoning will come, and it's a good trend, but latching it onto the existing models won't be enough. The other development that's been going on is what AI researchers call world models. These are predictive models for, well, the world. In the simplest case, for, say, the motions of objects in a 3D space. But once you have predictive models for any sort of data, you can also use them for more abstract ideas. Here is how John Le Coeur from Meta explains this.
I mean, first, the notion of world model is the idea that a system would get some idea of the state of the world and be able to predict sort of following states of the world, resulting from just the natural evolution of the world or resulting from an action that the agent might take.
And here is again Demis Hassabis about the relevance of world models.
First of all, you've got to build general models, world models, we call them, to understand the world around you, the physics of the world, the dynamics of the world, the spatial temporal dynamics of the world, and so on, and the structure of the real world we live in.
So I think what we'll see is world models combined with symbolic reasoning which can use large language models as a tool and not the other way around. And it'll probably take at least 5 years. Until then, we'll likely see some companies backpedal from AGI claims and instead get systems that are increasingly good at specialized tasks, like literature or web searches, but have no general intelligence. This is why I think Sam Altman writes that the path to AGI will be continuous rather than a sudden leap. It's to forestall people's disappointment when GPT-5 finally comes and isn't anywhere near human-level intelligence. But Dario Amode's expression, a country of geniuses in a data center, brings up an interesting question. What genius would voluntarily spend their life in a data center? Then again, what genius would voluntarily spend their life in academia? Thanks for watching. See you tomorrow.